Hello guys, this is the first presentation on Monte Carlo methods, and today I'm going to prove the following problem. So let u be a random number chosen between 0 and 1, and suppose that u is written in the following binary form. So the binary digits are b1, b2, so on, chosen from the set of two digits 0 and 1. And then the random number u has the continuous uniform probability distribution if and only if all binary digits bk are independent and identically distributed Bernoulli random variables with the common probability of success 1/2. So first I'm going to prove the necessity. Okay, so suppose that u is a uniform random variable, standard uniform random variable chosen between 0 and 1. Okay, and let's consider its binary digits. So if you look at the first digit, say b1 can be 0 or 1, so b1 is 0, and this happens if and only if u is between 0 and 1/2, and this happens with probability. Clearly, probability of this event is 1/2. Okay, since u is uniform random variable and the probability is equal to the length of this interval, which is 1/2. Okay, so analogously we have that b1 is 1 if and only if u lies between 1/2 and 1, and again the probability of this event is exactly 1/2. Okay, so now let's consider the second digit, say digit b2, and then again there are two possibilities for the digit, and say let's consider the case that b2 is 0. So b2 is 0, and this happens if and only if u has the following form. Okay, so the first digit can be any digit, then we have 0, and then we have other digits. Okay, and in this case there are two possibilities for b1. So b1 can be 0, so in this case u with the following form. Again, where you can with the binary representation 0.00 b3 and so on, or u equals this number 0.10 b3 and so on. Okay, so let's consider the first case. So in the first case, the first two digits after the binary point are zeros, and then the lowest possible number of this form is obviously the number that all digits are 0. Okay, so in this case u cannot be less than 0, so 0 is the lowest possible number, and then the largest possible number is the number where we have all these unknown digits are all ones. In this case that number u will be just nothing more but 1/4. Okay, so in the first case u has to be between 0 and 1/4. In the second case, again, there are two extreme cases. If all digits are zeros, then u is equal to just 1/2. Okay, if all digits are ones, then u equals 3/4. Okay, just remind you that so 1/4 can be written in this way, so 0.01. 1/2 is written in this way, 0.1, and 3/4 0.11. Okay, or it can be written in this way, 0.10, and then we have a tail of ones, infinite tail of ones. Okay, all right, so in this case what is the probability? So the probability that b2 is 0 is equal to actually the probability that u belongs to the union of two intervals from 0 to 1/4 and from 1/2 to 3/4. Okay, so the total length of these two intervals is 1/2. And since there are only two possibilities for b2, the probability that b2 is 1 is also 1/2. Okay, so acting similarly, we can prove that any digit is a Bernoulli random variable, and the probability of success, the probability that bk is 1, is 1/2. Okay. So indeed, okay, so how we can write? We can write that digit bk is 0 if and only if that number u lies in between the following numbers. Okay, so for some digits b1 so on bk minus 1, okay, we have the following inequality. For some digits b1 so on bk minus 1, again selected from this set. Okay, so if you consider this interval, so the length of this interval is actually 2 to the power minus k. Okay, so it's easy to see. Okay, and then for the first k minus 1 digits, there are 2 to the power k minus 1 choices, right? So the probability that bk is 0 equals, so you need to take a sum over all these possible choices. Okay, and for each choice, and clearly all these choices are independent and mutually exclusive, and for each choice the probability is equal to 2 to the power minus k. Okay, since there are 2 to the power k minus 1 choices multiplied by the probability, we obtain that the final probability is 1/2, and bk is 1 with again the probability 1/2 as well. Okay, so now how we can prove that these digits are independent? Okay, so we can prove for any s and k, okay, such that 1 is less than or equal to s less than k, bk and bs are independent random variables. Okay, so then we can prove that for every 3 digits we have the independence, for every 4, and etc. Okay, so for example, how we can prove that the first 2 digits are independent, right? So b1 and b2. So to prove that, we need to show that the probability, let's say b1 is I and then b2 is j for some digits I and j, is equal to the product of 2 probabilities. Okay, for every possible choice for I and j. Okay, so the right hand side, you already know the answer, right? Because it's supposed to be just a product of 2 1/2, so it should be 1/4. So we need just to show that the joint probability is equal to 1/4. Okay, so for example, how we can find the probability that b1 and b2 are both 0? Okay, so this happens again if and only if, okay, u has the following binary representation 0.00, and then we have other digits. Okay, so in this case u, again, for the considering 2 extreme cases, all of these digits are either 0 or all of them are 1s, we can obtain the inequality for u. So u has to be in between 0, okay, and then the other extreme case is 1/4. Okay, so the probability is 1/4. Okay, so now let's see, we can find the probability for every other choice. For example, b1 is 1 and b2 is 1. Okay, and this happens if u has this presentation, and this happens again if only if u is between 3 quarters and 1. So by taking all digits once, what we obtain? We obtain a number of this form, 0.1, 1, and so on. Okay, which is again by definition is given by this infinite series, and it's just geometric progression, which is equal to 1. Okay, so that's why for the other extreme case, then all these digits are ones, we obtain this number, which is 1. So the right end point is 1. Again, the length for this interval is 1 quarter. Okay, so for every case, we can obtain that the probability is 1 quarter. Okay, so that means that for every I and j, we have that inequality, hence these two digits b1, b2 are independent. Okay, so considering just some digits bk and bs, we can write down that probability that bs is I and the probability that bk is j equals, and again we have to consider different choices for other digits, right? So we need to take digits, all digits excluding bs and bk, and that all digits that follow them. Okay, so we have b1, so on, bs minus 1, bs plus 1, so on, bk minus 1. So all these digits are selected again from the set 0 and 1. And then when we fix this collection, we obtain some choices for the first k digits. Okay, and then the other digits may vary. And again, in this case, the probability of this event, so if you fix the first k digits, the probability of this selection will be 2 to the power minus k. Okay, so if you look here, in this sum will vary k minus 2 digits. Okay, so for each digit there are 2 choices, hence there are 2 to the power k minus 2 choices for this collection. Okay, so for each choices the probability is the same, 2 to the power minus k. So by taking the product we obtain 2 to the power minus 2, so it's 1 quarter. Okay, equals 1 half times 1 half. Okay, so it equals 1 half times 1 half equals the probability that bs is y times probability bk is j. And it's true again for every I and j. Okay, then again considering a similar problem, a similar solution, we can prove that for every choice of 3 digits we have a similar inequality, right? Okay, so for example we can prove that probability, say, bk is I, bs is j, bl is m equals, again we have the product of 3 probabilities. Okay, and so on. So that will prove that all these binary digits are mutually independent. Alright, so now actually that we proved the first part, so we proved that if u is a uniform random variable, then all its binary digits are independent Bernoulli random variables.